Let's take a look at another example, also related to those two examples, but building on them. So example 3, let's say you have a signal xt equals exponential minus at when t is positive, and minus exponential minus at, sorry, plus at when t is negative. If we plot this signal, again, when we have t is positive, we have this exponential decaying signal. This one. But when t is negative, we have exponential also decaying because of this negative here. So it starts from, when t is minus infinity, it starts from 0. So it starts from somewhere here, and then decays until we reach t equals 0. We hit the -1 here. Something like this. And if you look at this signal, it's an odd signal. Because of the symmetry here around the origin. But in the previous case, it was around the y-axis. That's why we call it an even signal. In this example, we have an odd signal. Let's have a look at its Fourier transform. What I'm trying to do here is just to give you some hints before the next lecture, where you will study the properties of the Fourier transform, similar to what we did in the Fourier series. When the signal, let's say for the Fourier transform, when the signal was even and real, we get an even and real Fourier transform. Let's see what we'll get for an odd and real signal. The Fourier transform here is, again, integral minus infinity to plus infinity xt exponential minus j omega t dt. The signal is defined piecewise, so this integral will be split into two parts. The first part from 0 to infinity, exponential minus at exponential minus j omega t dt, plus from minus infinity to 0, we have minus exponential at exponential minus j omega t dt. And this is actually similar to what we had here, but we have, the only difference is this negative sign between the two terms. So the first term will be 1 divided by a plus j omega. We'll have 1 divided by a plus j omega. The second term will be also similar to what we had before, 1 divided by a minus j omega. But we have this negative sign here, 1 divided by a minus j omega. And if we combine those two fractions, we get a minus j omega minus a plus j omega divided by a squared plus b plus omega squared. And this will be, those will cancel now. The real part cancels out, so the only remaining term is the imaginary. So we have minus 2 j omega divided by a square plus omega square. Now, notice that the Fourier transform this time is purely imaginary, and it's odd. Okay, so when the signal is real and odd, Fourier transform will be odd and imaginary. And if we plot this one, if we plot the magnitude and the phase for this Fourier transform, xj omega, now the magnitude of x j omega will be just the absolute value of this term. This is real and positive, so divide by a square plus omega square. Okay. And if we plot this, versus the frequency omega, when omega is 0, we have 0. And then when omega is positive or negative, we'll have two symmetric parts. One of them will look like this. Then we have similar on the other part. And this is similar to what we call a bandpass filter, because it's passing, it's allowing only the frequencies in this band to pass, and everything else will be degraded. We plot the phase of this frequency transform. If you calculate the phase for this signal, you will get this minus pi over 2 or pi over 2. This when the omega is positive and when omega is negative. If we plot that, get this here, this pi over 2, this negative pi over 2. This is the phase of x j omega, and we're plotting versus omega.